And that's for this week because I hadn't told you before. Now, when I was talking before, Mr. Hodges had tried to let me know his thoughts on the matter, right? I was going to tell you that that is starting next week because the hope is that by next week you would have been even faster at this. The hope is also that the information will come to you before and you will have time enough before to look at it and be able to get your background information, make sure you understand the concept. You would have seen the data already, so you would know, even if you don't know the particular one that you're going to be working on, you would have seen the data. You can do some quick evaluation on any one of them and be able to know what to expect. So that by the time you come to the session, it would be, instead of it being me trying to explain something to you, it'll be more of a quick discussion just to make sure everybody is on the same page, and then you go off into evaluation, and then I come in and help you as necessary in a little concept area that you may not have fully grasped. We work it out, and then hopefully by the end of the session you won't even need a 5 minutes after to do any tweaking, but you would still get the time. But that's just for fine tuning.
Yes, just a question. How many more lab reports do we have to do, overall?
So you've completed, by the end of today, you would have completed, well, by the end of this week, you would have completed 7, right? Usually in the face-to-face, and yes, Mr. Hodges, roll your eye because I'm saying usually in the face-to-face, usually in the face-to-face, it's about 9 experiments for the semester, right? 8 to 9. In the online, because of the fact that it's online, usually the number of assessments will be more. But we're already at week 9, so we have a total of 7 more weeks to go. So I cannot, I assume Mr. Simpson has plans for another 3 to 4, well, probably 4 more of these. Is it that you would like a break, Mr. Humphrey?
That would be appreciated.
So is it that you want the break at the end or in the middle?
I guess that would that would have to be a unanimous decision among the class members.
No, you can suggest. I'm almost sure that what you suggest, everybody else would be in agreement. So go ahead and let me hear it. I'm not promising anything, but go ahead and let me hear.
I would say that the break should come at the end, but as I said, I can't really speak for all of the class. So, guys, what do you think?
What do you mean by the break, Miss? And the middle? What do you mean?
Oh, I only meant a one session off away from me. So it's either a matter of you wanting it, like you don't want to see me next week, or you just want to get it me over and done with, and then have the last week or two to yourself.
I know, just really love them and get it over with. That's on
Yes,
me.
we
Just
go and get it over
get
it.
it over with.
Okay. So it's
If
for the most part. Yes, Mr. Morgan, go ahead and what you're saying.
all right, I sent you an email. You can check it, please.
Okay.
It's about my situation.
Okay. All right. Well, I won't be able to do that quite yet. So for the most part, it does sound like you would prefer to run through the sessions. So I will go ahead and present that to Mr. Simpson, and we'll work out something that is reasonable, that would allow you enough time, more than likely towards the end. So because usually at the end you'll have some final assessment, some projects that will be due, and those sort of stuff. So let me see how we can work so that towards the end you'll have time to use our sessions. Not necessarily that you will have them to yourself, but you may be able to use them to do something other than our exercises.
Right, Miss. Right.
All right, no
Miss,
problem. That's Mr. Miller. Whoa, Mr. Miller, I haven't heard you in a while.
Mrs. Miss, you said 7 week, Miss. You did 4 more weeks left, Miss. Next break.
All right, I didn't hear you. Sorry.
You said that 7 week left, miss, in the semester. Isn't it 4 week with 1 week separate?
No, remember online semester is different from the regular semester. So it's a 16-week semester. There is no break. So usually in the face-to-face, what would have happened? You'd have had 13 teaching weeks, then you would have had 1 week study break, and then you would have the remaining 2 weeks where you would actually have your final assessments. For regular face-to-face, they call it exams. With online, it's called assessment. So you would have had your final examinations in the 2 weeks after the study break, right? For the online delivery, unfortunately, there's no study break. So it is a 16-week semester. It runs from week 1 straight to week 16. So as a result, you will find that you may not have a final exam. You may have a final assessment, but that final assessment, it won't necessarily be something where it is 50% of your grade, as in the regular face-to-face. So the regular face-to-face, it would have been a final exam, right? So you're under full-blown exam conditions, and it would have been worth 50% of your overall grade. With the online, the assessments have changed, so as a result, you will find that you don't necessarily get a break. You have continuous assessments throughout the semester. Well, you should have had continuous assessments throughout the semesters. You would have had an increase in the number of them, so you would have had to be doing more assignments, more overseen assessments, as well as more projects, and you will find that even the exercises, the laboratory exercises, because you're not doing them face to face, the number of those would also increase. But that's what should have happened. I can't say what has happened for some of your courses. All right. So yes, that's that, Mr. Miller. So let's talk about today's experiment quickly. It's a very nice and short one, and then I'll let you go off. And I will be sharing my screen now. So, okay, thank you very much for that. Okay, so screen sharing will begin now. So you should be seeing in front of you my screen, which has experiment 7 written up on it, and it's all about waves, and this particular one is light intensity we're looking at. So you know, and this is just a quick run through, you know that there are different types of waves. You have 3 types. You have mechanical waves, you also have electromagnetic waves, and you have what is called matter waves. Some of you may have been exposed to matter waves, some of you may not have been. For the purpose of your course though, you will only focus on the 2 main types, the electromagnetic ones as well as the mechanical waves. You would have known that mechanical waves require a medium. So you would have learned about that you have in the mechanical wave version, they also have stationary and traveling waves. You would have learned about different types of waves as well. Another way to categorize waves would be not only whether they're moving or stationary, but whether it is that they're transverse or longitudinal. Where transverse means that simply the particles in the medium are displaced perpendicular to the direction of travel of the wave motion. Whereas, for instance, in the longitudinal version of waves, the particles are displaced in the direction of motion of the wave. Now, you would have known for sure that a wave is simply a phenomenon, it's not an object. It simply allows the transfer of energy from one location to the next, right? So an electromagnetic wave is one of those types of waves that allow energy to be transferred from one point to the next, right? Amongst it, you would have also learned that in the electromagnetic wave, there is a whole spectrum of, one second, let me Mr. Savvy. So in the electromagnetic waves, you would have had this entire spectrum of different types of waves that fall in. You would have heard of the FM waves, the AM waves. So you, even though you would have thought that radio waves are sound waves because you're listening to them, radio waves are electromagnetic waves. They just have sound that has been modulated on top of them for transfer of energy, right? So your FM, like I can't remember what's that modern station you guys listen to these days. So I listen to Cool FM, and then I think you get, my son listens Zip, right? Zip 10, is Zip 103? I think it's Zip 103.
Or Miami
Higher?
105.
I've never heard of that one.
No man, I will.
Okay. Well, thanks for that. I'll check that one out and see. 105. So you have these FM, that's frequency modulation, and those are electromagnetic waves. You also have in the same spectrum, you have the visible portion of it, the one that we are able to see. And in that visible portion, you have different colors because that allows us to be able to see our colors. So these all have different wavelengths, different frequencies. So within that spectrum, now you have starting from your red all the way up to your violet. Right? Those are the 7 colors, and you have combinations of these that can give you different visible light that you can see, visible electromagnetic waves that you can see. And if, for instance, you have all those colors, the 7 of them, and I know I don't need to go through them because you learned them from you were in grade 2, right? You would have known that once it is that all 7 are combined, what you get is an absence of color. You have what is called white light. Now, beyond those, you have, for instance, ultraviolet, you have X-rays, the gamma rays, these that you use to help with, X-rays are used to help you observe within your body, and you have like gamma and X-rays are also used in chemotherapy, not chemotherapy, in radiation therapy, right? So you have all these different waves with their different wavelengths within the electromagnetic spectrum. However, we are going to be focusing in this exercise on the waves that fall in the visible portion, and we call those light waves, right? So here's the thing about it, the intensity. Remember, intensity has been defined, and Mr. Simpson would have told you, as the power per unit area. So once you have a light source, that is a source that is emitting light energy, that is emitting electromagnetic waves in the visible portion, right? Usually the source emits it radially. So it emits it in a spherical fashion. So once it is a 3-dimensional source, then you can expect that the radiation will be 3-dimensional and it will be spherical. Now, intensity is a measure of the radiation. It tells you the amount of power per unit area that is emitted. Now, power is your rate of change of energy. It's the amount of energy disseminated, transferred, absorbed, or whatever you've done with that energy. It's the amount of energy per unit time. For light source, it's the amount of energy that is radiated or disseminated per unit time. So when you talk about intensity, it's the amount of energy per time per cross-sectional area, per area of dissemination. So you know the cross-sectional area of a sphere is 4 pi r squared. You remember that, right? And the volume of a sphere is 4/3 pi r cubed. Remember that? So let's talk about it. So power is your energy over time, you know that for sure. But intensity I, and using I for intensity, is going to be the amount of power per area. If it is that the area that is being considered is in the form of a sphere, right, or has a spherical orientation, then clearly the cross-sectional area will be that for a sphere. And you would therefore know that the area for the sphere is going to be 4 pi r squared, right? So if you look carefully at this, then we can factor out the two variables, because once it is that is just a simple light source and you are not changing the voltage that you've applied across the terminals of it, you're not changing the power supply, in other words, then, and assuming then that there is no conversion within it, in other words, no dissemination of energy as it is radiating, that even irrespective, no net dissemination. So whatever energy gets out, that's the energy that is going to be emitting, right? Once there is no net energy dissemination, what will happen is that the power will remain constant. It won't change per time. So in this case, you will notice that the only two things that would vary would be the intensity and the radius of the sphere around the source. And that radius is going to be the distance away from the source itself, because in that case, the source will now be the center, and if it's the sphere around, then any distance d away will be the radius of any sphere around the source. So you will notice in this case that you can factor out the constants, which will be p over 4 pi, and that will leave you with the variables, right? So clearly, based on this, you can see that the intensity will change as you change the distance or change the radius of the sphere, which is really the distance away. You will then notice clearly that as the distance increases, the intensity will reduce. This is no proportionality. You can see that this is 1 over r squared, which then is an exponential relationship. If you square the distance and increase that, you will find that, so in the first place, there's an inverse relationship between the distance and the intensity. So as the distance increases, the intensity decreases. When you square the distance and increase that, you now have an inverse proportionality, right? So the intensity is inversely proportional to the square of the distance, right? So not even though you increase the distance, intensity reduces. The proportionality comes in once you square the distance, and that proportionality is an inverse proportionality. So that being said, you are now going to be looking at this simple experiment, right? Here you have the light bulb as a source. It's going to be three-dimensional. That means that the intensity will vary in a spherical manner around it. Here is a light sensor that can detect the intensity that is coming from any particular source. So what this sensor would allow you to be able to do is it will, once you put the sensor at some distance away, you can measure the intensity. Measure the distance is no problem because that's an easy thing. You use whatever measuring device you have, whether tape measure or ruler, and you'll be able to determine, well, in this case, you have a meter stick. So very simple setup, and so that you're able to measure not only the distance, but the equivalent intensity at that distance. So in this experiment, what would have happened first is that you would have just put the sensor, turned it on without turning on the bulb. So you put the sensor at a distance, anywhere, it doesn't matter where in the room, just think, and you would have then been able, because then you would have had a diffuse source rather than a specific source. And once you put the sensor without turning on the bulb, you will get a background reading. That will be your background intensity. That's your I naught that is here in this write-up. Then you would have put the sensor some distance away from the source. The bulb, turned on the bulb, turn on the sensor again, as if you had turned it off, and then you would have taken note of the intensity as well as the distance away from the source. And so you would keep moving the distance and taking note of the new intensities at the different distances. And once you've been able to collect all of that information, you will now find yourself with information about the background intensity and the different intensities at different distances away from the source. And you will be able to know, because once it is that you have two variables that depend on each other. Well, one that depends on the next, or even if both depend on each other, depending on the concept, you are able to plot a relationship, right? Once it is that you generate any graphical illustration of that relationship, you are now able to do some evaluation on it. If you do a plot and you get an exponential, then you can go ahead and explain what type of exponential relationship. Is it an inverse or a positive exponential relationship, and those sorts of stuff. If you get a straight line one, you can do even more than talk about the relationship. You can say, yes, I have gotten a linear or a proportionality, whether it is positive or negative. However, you are also able to do further. You can use gradient calculations to get other information. You can use intercept determination to get other information. So the straight line graph gives you so much more, not just a visual representation of the relationship, but allows you to do further calculation. So that's why it's always nice to be able to present information in a way that it's represented by the straight line curve that you can get further data or further information from, right? So you will, in this particular exercise, and let me pull up what the data will look like. So this is group 7's data that we're looking at. You would have seen here that I have provided you with some sample title, and that's not anything for you to be to use. It's just that I wanted to write it, so I wrote it. So you will also notice that the original data, the labeling, I've left it because I want you to recognize that you don't provide this information as is. You are going to go ahead and change it, so you don't leave it with d meters. You're gonna write out the distance, or if you think it's a displacement, you write it out as displacement, which I'm sure you'll know it's not really a displacement, it's really just a distance anyway. So you will go ahead and label it appropriately, each of these. You're not going to write 1 over distance, that's not a word. You write inverse distance, you tell what it is. Please note that I expect that by now you know the difference between a negative relationship and an inverse. You know the difference between a negative proportionality and an inverse relationship. Inverse relationships are not proportional. Negative relationships can be, as well as they cannot be. So negative just tells you if one increases and the next decreases, whereas inverse tells you yes, as the next one increases and decreases, but it's exponential. All right, and you won't write this as 1 over this distance squared. You will write this as the square of the inverse distance, or inverse distance squared, or distance squared inverse. So you are going to specify exactly what was here, and you will notice that the arrow that is here, which is meters squared, you know that 1 over d squared will not have units of meters squared, but will have units of m to the minus 2. So even though I've gone ahead and pointed it out, you should have been able to observe it enough yourself. So you have this data here which gives you the different distances and the associated light intensities, and the units is in lux. You also have the background intensity that's provided in row 21, and this one is 1950 lux. And if you check all of them, they have the same background intensity because they were all performed in the same environment. Same background intensity of 1950 lux. So you're supposed to not necessarily complete this table. Yes, Mr. Hodges.
Yes. Could you just explain what is the background light intensity? Where does it come from? Yes.
Oh,
that's the initial. Go ahead.
As you are right where you are, right?
Right.
That's above your head, right?
Right.
Suppose you had your windows open, that's going to be sending in light as well, right?
Right.
And but suppose you wanted to observe the intensity variation of the bulb above you with the
Right.
distance away, you would have first had to know, because when you measure the intensity, it's gonna give you what is coming in from the windows, what's coming in through your door, plus
Right.
what's coming in from your light bulb. So to get the background, you would have turned off your light bulb, and that would have told you what everything else is pulling in. And so that's
Right.
background intensity. So once you
It's
turn
just
on
that
the
the
bulb,
initial.
that's not so your initial reading would have been that first distance when you turn on your light bulb, but that's
Right.
your background. Your background is what is there without your bulb being on.
Okay.
So
Okay.
then when you turn on the sensor, it's gonna take in not just your light bulb but what's in the background. So you need to
Okay.
mind.
Mine is that. All right. All right. Okay. Thank you.
No problem, Mr. Hodges. So when you're generating, you can choose to generate one table or you can generate three tables. Take note that you're required to do three graphs. The first graph is you're going to do corrected intensity. That means you're going to minus the background intensity from any intensity value, and then you're gonna do that plot versus distance. The second graph you generate is going to be the corrected intensity, which is the background from the specific intensity versus 1 over the distance, the inverse of the distance. And then there's a third graph where it's the corrected intensity versus the inverse of the squared distance, right? So three graphs. So you can choose to generate three tables for the three different graphs. However, each table must have enough information to generate the graph. So even the third graph, you can't just give intensity and then give distance squared. I mean inverse distance squared. You actually would have to provide the background data, which would have been the intensity and the distance, and then your third column could be the inverse of the distance squared. So you still have to provide the base information irrespective for each table that you're doing. You can be concise and efficient and just provide everything in one table. And
Miss,
yes, Mr. Morgan.
I was asking to go back on the data. And with that data, we should get all that information.
Well, the data that's provided to you will have the distance and the light intensity. So if you're doing three tables, all three tables must have this fundamental data.
Right, all right.
But if you're doing one table, it would look something like this. However, you would position it appropriately. For instance, you would, if you wanted, you would keep all your intensity data to one side and put all your distance data to the next side. So you would have shown the manipulation on your different distances. So you may choose to say, all right, I need to manipulate distance, I provide the fundamental distance data, then I provide the inverse of the data, and then I provide the inverse of the square of the distance, right? And then after that, now I present the intensity data, the main intensity is collected from the sensor as well as the corrected intensity. So you know, in your efficiency, will find a way to put the information that is nicely and easily understandably flows, and the individual won't have to stress him or herself, which would be herself because it's me. But you, as an engineer, your task is to do all the work and make sure that it is easy for the user. So same when you come up with your phones are easy to use because the engineers did the work to make sure that it has all the different codings and all the codings work well and they work in a particular time frame. So when you press it to press A, the code that requires A to come up on the screen does so within no time, right?
Miss,
Yes, Mr. Morgan.
so if we should get a y-intercept, that would be the background intensity, right?
So let's talk about. So let me go ahead and show you. You are doing corrected intensity versus R squared. If you look at this equation, right? This is if you do it in the form of y equal mx plus C, then in this case, if this is the corrected intensity, then you realize that you have no intercepts. Okay?
Right.
However, if you are simply doing I versus, so if instead you had I minus I naught is equal to P over 4 pi squared 1 over R squared. So then in this case now you would be able to put it over, you would know intensity is going to be P over 1 over R squared.
Yes, so why the pi squared?
Why?
No, 4 pi r squared.
Oh, my apology. I'm so used to writing.
Pi squared.
Yeah.
Sure.
Thank you. Oh, I don't know why my brain went to that. What was I thinking about? Waves. Yes, that's the problem. Okay, so here we are, right? So in this case, Mr. Morgan, if you were just doing the intensity without taking out the background, right? Then you would have been able to get an intercept which would have been your background. Do you understand?
Yes, miss, I'm getting that.
Okay.
But alright, we don't. Banana, sir. Hold on. Would you need to plot a graph as such then
Would you need to photograph what?
of this what you just represented me?
No, this you're not doing this one. I was
Oh, okay.
showing you that if you were, because you asked about the background and the intercept,
Right.
and I was just explaining what in which situation you would have had the intercept, but because you are going to be doing corrected intensity versus anything else, you won't have an intercept.
Alright.
Well, you
Thank you.
shouldn't. But if you do, you already know as having been through our course or session so far that anytime you have something that is not what you should have, what you expected, you need to figure out why and explain it.
Right.
Okay. Okay, so this is what you'll be working on. Any questions before I assign you? Okay, that means we're all good. Nice and easy experiment today.
Okay, I know you probably won't want to answer this, but in relates to this lab, let me go back to the aim. What's the aim again? Sorry.
Oh, you were totally correct when you
Just
said
a moment. Let me go to the aim. Investigate. So to investigate the mathematical relationship between intensity and the distance from a light source. So with that aim now, we're supposed to find just the gradient in relate to that for each of the graphs.
You're going to find a mathematical relationship. In order to find a mathematical relationship, that means that you need to write an equation. And in order to write an equation, that means that you need to find all the different constants and variables for the equation. So if I should write an equation that says that z is equal to 4q plus 5m, this is me writing the mathematical relationship. If 5m is a constant and q is a variable and z is a variable, then clearly in order for me to write this equation, first I would have to find the intercept and I would also have to find the gradient. So writing a mathematical relationship requires that you're going to write an equation. And in order to write an equation, that means you need to know what are all the constants and variables in the equation.
Okay, mate. Thank you.
You're welcome.
Which simply means that you need a straight line. graph, right, miss?
Well, I'm trying to, let's see now. Can you, you don't, I'm sure you don't know how to, yes, you will need to, for your purposes, you will need to, and that's why I explained to you in the first place, is the straight line graph that allows you to be able to get further information. Whereas the others only give you a graphical or illustrative representation of the relationship. You can't do anything with it. You can't write a relationship until you do that straight line. And it's a straight line that lets you allows you to be able to do further. Does that answer your question? It's all right, yes. You have to get a straight line graph. All right, so give me a few, let me check and make sure that I have everybody. And I don't see you, Mr. Scott. I don't see you, Mr. Let me check the chat first. Mr. Morgan, you wanted that question ignored now? What does the gradient 4 pi p over 4 pi mean?
Yes, miss, I'm still asking at the moment.
Okay. So the only person
Miss, I'm still asking, you hear me?
you're still asking up, oh, who spoke? Oh, Mr. Morgan, you're still asking what? What does
About the, yes.
what does the gradient represent?
Or you just, wanted to get the equation?
Remember, no, you just need to get the equation. But if
Alright.
you wanted to to think that maybe I would be willing to consider bonus points, which usually I'm, but if you were thinking along those lines, you would have said even further that the power clearly in this case is equal. So you would have gone that one extra step and hope that, I was one of those lenient considerers.
But you're not talking like you're one of them.
Not really. But I did give bonus in the last lab, so. But those worked for it.
Mm.
Oh no, no problem at all. You didn't have to leave. Okay. You don't have to leave. The individual who sent me the private message. All right.
Yeah, WhatsApp me.
Excuse me, Mr. Morgan.
Well, so Michelle just WhatsApp you instead of emailing me.
How would you WhatsApp me again?
Oh, Michelle, alright. Oh, you mean private message on the Zoom call? Shall I send that then?
What was that?
Don't worry, Miss, we just have to figure out.
Okay. Oh no, I meant private message in the chat. Certainly no WhatsApp call at all. So let me check to make sure I have everybody. So, Mr. Humphrey, I see you. Mr. Hodges, we've spoken and I see you too. And then there's Miss Barnes. No, I don't. Yes, Miss Barnes, I see you again. Then we have Mr. Miller. Yes. And then we have Mr. Sterling. Still here. Mr. Sterling, I'm not seeing you again.
Miss, but I'm still here.
Oh, that's where you are. Okay. And then Mr. Vajay Scott. Okay, I see you. And then Mr. Adrian Lawrence. Yes, I see you. And then Miss Tiffany Someone, I see you. And Mr. Jonathan Johnson. Okay, thank you. Mr. Yasan Chin. Okay, I see you. Mr. Alroy Horn. Okay. Mr. Joel Wisdom. Oh, there we go. Yes, Mr. Wisdom. Miss Richards, are you still here? Miss Dana Richards? Okay. She's gone. Miss Deidre Meek? Oh, yes. Mr. Shemar Morgan, we spoke. Mr. Javar Sitong, I see you. Mr. Damali Swaby, I see you, Mr. Swaby. Mr. Josh Blake. Mr. Blake? Oh, there we go. Mr. Matthew Brown. I'm seeing you, Mr. Brown. Mr. Brown. So we'll put you aside for now. Mr. Alandre Thomas. I see you, Mr. Thomas. And then, is there anyone that I've missed? Mr. Curie Thomas.
You say miss me too?
Who could I have missed?
Davis.
Oh, Mr. Javier Davis.
Didn't hear my name because I had some connectivity issue.
Okay, I kept calling you Mr. Brown. So I'm glad you returned. Is there anyone whose name I have not called? Okay. Alright, so in that case, for group 1, we have Mr. Dominic Humphrey working with Mr. Kieran Hodges. For group 2, we have Miss Morgan Barnes working with Mr. Leroy Miller. For group 3, that's Mr. Adili Sterling working with Mr. Reggie Scott. For group 4, that's Mr. Adrian Lawrence working with Miss Tiffany Salmon. Group 5 will include Mr. Jonathan Johnson and Mr. Yasan Chin, whereas Group 6 has Mr. Alroy Horn with Mr. Joel Wisdom, and I will repeat at the end. Group 7 will have Miss Deidre Meek with Mr. Shamar Morgan, and Group 8 will have Mr. Javar Sitong working with Mr. Damali Swaby, whereas Mr. Josh Blake will work with Mr. Alandre Thomas in Group 9, and Mr. Curran Thomas will work with Mr. Javier Davis for Group 10, and Mr. Matthew Brown will be working on 11, working as Group 11 by himself, right? So that's your misfortune today, Mr. Brown. You'll be working by yourself. However, I will I'll ask a group to facilitate you sitting in with them. I will go to the group privately, ask them if they will mind you sitting in. And if they don't mind, then I will assign you to work with them. All right? So group 1, Mr. Humphrey, Mr. Hodges. Group 2, Miss Barnes and Mr. Miller. Group 3, Mr. Sterling and Mr. Scott. Group 4, Mr. Lawrence and Miss Salmon. Group 5, Mr. Johnson and Mr. Chin. Group 6, Mr. Horn and Mr. Wisdom. Group 7 is Miss Meek and Mr. Morgan, Mr. Shemar Morgan. Group 8 will be Mr. Tom and Mr. Swaby, whereas Group 9 will be Mr. Blake and Mr. Alandre Thomas. Group 10 will be Mr. Curran Thomas working with Mr. Javier Davis, whereas Mr. Brown will be working in Group 11. So, give me 2 seconds in the meantime. You can have a mental break whilst I go ahead and create your rooms.
Mental break, I call it.
Yes, Mr. Hodges, because I'm not talking, so it's a mental break from me.
All right, man.
Thank you.
Was that sarcasm, Mr. Morgan?
No, miss, I'm truly grateful.
Sure, I'm sure about that.